Let's welcome.
It's a pleasure to be here and a little bit intimidating to see my name among the distinguished speakers. Yeah. Okay. I will talk about a subject I'm personally involved in, and it's a conformal geometry, and essentially mainly talk about the development in four manifold. So although everybody here knows, let me just recall what conformal geometry means. Conformal means given a metric G, we take a change by multiplying the metric G by a positive function. And to emphasize this is a positive function, we sometimes denote this by exponential 2w. So this is a metric, and the conformal refer to angle preserving property. That is, the two vectors in G hat and G are of the same angle, just stretch the length. So there are many problems in conformal geometry. I'm basically talking about using PDE method, and the relevant thing is the sign of the curvature, the size of the curvature, and then the sign, as we will see in this talk, the integral of some curvature quantity. And the conformal geometry is study how this conformal invariance terms, which are invariant under conformal change, either pointwisely or in this integral sense, and to use that and the relevant conformal invariant operators and to study geometric property of the manifold. So my talk, I will first review, since everybody knows a Gaussian curvature on compact surfaces, and briefly talk about Yamabe problem. And then I talk about conformal invariance on closed four manifold. One particular curvature I will talk about is a sigma 2, and which I will explain, and some Q curvature. The difference between these two is in terms of PDE, sigma 2 is a fully nonlinear PDE, while the equation associated with Q is a linear PDE, but of fourth order. And then I talk about some geometric content of this. And then I talk about some general GJMS operator and curvature, and in a special setting that's in conformal compact Poincare-Einstein manifold and via scattering theory. And then I would put a main application is talk about the problem of conformal filling in by Poincare-Einstein metric. I will address the conformal compactness problem and the existence problem. Okay, so a very brief review on two manifold. We have the Gauss-Bonnet formula. So the left-hand side is a topological quantity. The right-hand side is the curvature and analytic property. And then, of course, we have the uniformization theorem. That is, depending on the sign of the integration of the Gaussian curvature or the size of the Euler characteristic, we can essentially, up to isometry class, classify the two compact surfaces. And then for PDE point of view, if we change G to GW, we are talking about a linear PDE, which has this nonlinear term exponential 2W, and that is a prescribing Gaussian curvature of KGW with G, with W, the original metric G. And a variational approach to study this problem is well studied, and that's by this Moser function of J. And one study this and talk about the critical point of this, and then we get KGW equal to constant and variational problem of prescribing KGW. That's called Moser functional. And this Moser functional turns out to have another important geometric interpretation, and it turns out this is the difference of log determinant of minus Laplace vice minus GW, the quotient of that. And this is the log determinant in the sense of Ray single zeta function regularization. Okay, and now if we try to generalize this beautiful piece of work to high dimension, one attempt is to study the so-called scalar curvature. And the Laplace operator is replaced by conformal Laplace operator. And then we want to, this operator has the conformal covariant property. That is this R hat. Now, the traditional notation of this conformal change is u to certain power, 4 over n minus 2 power. In terms of that, we can prescribe R hat using this PDE. That's called the Yamabe problem of prescribing R. And this problem turns out to be variational. That is, if we consider RG hat integration and take inf over G hat, if the metric which is in the same conformal class is a 10, makes scalar curvature constant. It's variational. And then the inf of this is called this Yamabe invariant. Yamabe constant, which is a conformal invariant quantity. And now if we look at the informed manifold, if we try to look at the Gauss-Bonnet theorem, it turns out there are two terms, the Euler characteristic and the Weyl curvature term, and then a second term, which is a combination of the scalar vice Ricci, but there's a minus sign there. Scalar square minus 3 Ricci square. And one particularly important property of Weyl curvature is this Weyl is a pointwise invariant. That is, okay. So first, if G equal to E2W, if the Weyl is equal to 0, that means locally the manifold is in a neighborhood the same as the flat, so R4 Sn. Okay, so this is a local conformal invariant property. And the other property is it's a pointwise conformal invariant. So if one interchange of this GW, one pull out a conformal factor. And it turns out if this will look like a D volume in full manifold, this pointwise invariant says the Weyl L2 known is a conformal invariant quantity. And so if one look at the Gauss-Bonnet formula, one have the topological information and the pointwise conformal invariant quantity. That means the next term is also a conformal invariant. And that's the term we call the sigma 2. I will explain the notation. So the consequence is this is a conformal invariant in full manifold. And now let me justify the name of sigma 2. Sigma 2 means second elementary symmetric function of what? Of a tensor. It turns out this is a so-called shortened tensor and studied in Cardan geometry. It's a combination of Ricci tensor, and in terms of this tensor of full curvature decomposed nicely of Weyl term and some A which with G is a Nomizu product. So there is these two terms. So let me say what's sigma 2. Sigma 2, sigma 1, sigma k. Sigma 1 means take trace of this tensor. So the trace of this tensor turns out to be scalar curvature. So the Yamabe problem is to study sigma 1 of the shortened tensor. And then sigma 2 means the product of lambda and lambda j. So that means the trace square minus the norm square take 1/2. And it turns out for this particular shortened tensor, the sigma 2, so-called second order elementary symmetric function happens to be our Gauss-Bonnet integral minus the y part. And sigma n, of course, is the determinant. Okay, and then since this sigma k of shortened tensor was first studied by Jeff Wielkowski in around 2000. And he mainly studied a subcritical problem where 2k equal to n. 2k less than the dimension. We are interested in k equal to 2, n equal to 4. So this problem is well studied, and let me not give a survey, but there is intensive study about existence, geometric property, and uniqueness problem. And the direction which have lots of progress is when this AG head is in the positive K cone in the sense of guarding. So in positive 2 cone, positive K cone. And only in recent years, they are beginning a study of negative cone. Contrary to the case K equal to 1, when K equal to more 1, the negative scalar curvature problem is well studied. But when K is bigger than 2, it's the positive cone problem. We have tools to study them. And for K, for negative 2 cone, we are short of C2 estimate. Okay, so let me still come back to study in 4 dimensions what the sigma 2 AGW equal to constant mean. So we change conformally GW, and then the leading order terms. The shortened tensor has 2 terms. One is hashing, and one is DW, which is DW, and so on. There is this explicit expression. And using that explicit expression, we can write down sigma 2 AGW E4W. And it turns out this integration of sigma 2 AGW E4W is a conformal invariant, but the highest order term of that is Laplace square minus Hessian square. But there are also some kind of lower order term. And let me remind everybody, if we study instead of shortened tensor, if we study hashing of U, then sigma 2 is just Laplace square minus Hessian square. So their leading order terms are the same. Okay, so we would like to study this sigma 2 equation, but when n equal to 4, this integration of this is a pointwise invariant. So under conformal change, it does not have any information. So we seek other methods to study this. Something like Moses function. The analog is Moses function. Okay, and it turns out the tool comes from the consideration of higher order conformal invariant. So I have already mentioned the conformal Laplace is a second order operator and has invariant property. It turns out in 1983, through the study of Maxwell equation, Penny studied this operator, which is a fourth order operator plus some second order term. The second order term has coefficient of curvature encoded, and then plus some curvature called Q4 curvature. And if one look at this equation, one realizes that this P4 on function 1 is Q4n, but this is only when n is not equal to 4. When n equal to 4, you do not see this Q4 from P4. And this P4 happens to be an analog of conformal Laplacian, that is, has conformal covariant property. And instead of n plus 2 over n minus 2, one has n plus 4 over n minus 4. And what the important observation or point of angle of Tom Bronson is Although Penny's only studied this P4 when n bigger than or equal to 5, n equal to 4 is actually more important. He's pointed out one can write down the operator P4 in 4 dimensions, and then there is still the Q curvature, which one can write down, and then this particular, there is no n minus 4 over Q there, but there is an operator, and it's a continuation when n tends to 4, and it satisfies this PDE. And this PDE is a complete analog of Gaussian curvature in 2 manifolds. So that means that this QG may play some role like Gaussian curvature in 4 manifolds. So for example, when R4P is just a bi-Laplace on a sphere, it turns out to be Laplace composite with conformal Laplace. Okay, so now we stare at this Q in 4 dimensions. It's a multiple of scalar plus sigma 2. We are interested to study sigma 2, but Moser's approach tells us we can study this Q curvature. So this Q curvature is linear 4th order curvature. One can study this operator. This is the analog of Moser's J function. And then what we are trying to do is we are trying to cancel out this Laplace R. And then we look at the functional which study Laplace R. That's the 3 functional. The variational equation is 3. So now we study 2 minus 1 12 third. And then that would cancel out this term, and we get sigma 2. And that's a basic data observation of myself and Paul Young and Brando Wiakowski. We say indeed this is the analog of Moser's functional to prescribe sigma 2. And then the approach to solve this question, at least one approach, is we play the variation. We look at 12 minus delta, and then that delta tends to 0. And then when delta is greater than 0, a certain range, this is a subcritical operator, the solution exists, and then we try to let delta tends to 0. So the analog of this is this homogenization process for hashing equation. Suppose we want to solve sigma 2 of hashing U. We add a 4th order term, a delta, homogenize it, and the delta tends to 0. So indeed, in 4 manifold, if we begin to consider 2 conformal invariants, one is the Yamabe invariant, one is sigma 2. If this 2 invariant has positive constant, it turns out this is if and only if there is a pointwise solution in the same conformal class, which is in positive 2 cone. This is an if and only if condition. And the surprising thing is if and only if. And then this sigma 2 is interesting in 4 manifold because positive 2 cone metric in 4 manifold is Ricci positive. So there are geometric consequences. Okay, so and that's all I want to mention about this the work a long time ago. But let me also point out the work of Gutsky and Street in 2016. They say that if we want to solve sigma 2 AGW on S4, of course, there's one parameter of solutions diffeomorphic to each other. But if the manifold is not conformally the same as S4, then the solution is unique, exists and unique. This uniqueness shows this metric is really the canonical metric in 4 manifold. Okay. The result is surprising, especially contrast to the work of Rick Shen, which shows that in S1 lambda cross Sm with product metric, when lambda is very big, the Yamabe solution is not unique. There are different solution, while for the sigma 2, the solution is unique. Okay, and now I will switch the talk to talk about some application of this whole idea of study Q curvature and then using the conformal invariant property. One problem I want to talk about is the problem of conformal filling in. The conformal filling in problem is, given a manifold MNH, we ask when does there can be Mn can be extended to Xn plus 1 so that Xn plus 1 has a Poincare-Einstein manifold. So we have Mn here, and then we have Xn plus 1 here. And then here we equipped with a G plus metric. That G plus usually is Einstein. And the relation is, if we look at some geodesic defining function or distance function, R squared G plus. So MNH is on the boundary, and we want R squared G plus is true to M is equal to the original H. So we ask, when does what kind of M allow such extension? That's the problem comes from ADS CFT correspondence. And it turns out this problem, this Poincare-Einstein metric, this conformal field, if one can conformally compactify it, then it's also asymptotically hyperbolic. And this is a problem well studied in geometry, asymptotic hyperbolic metric. Okay, so here's the definition. We have a defining function R, and such that dr is not equal to 0. And we want to find some R such that R squared G plus restrict to the manifold is H. And since this R is by no sense, this defining function is by no sense unique. So we can multiply R by any positive function and get another defining function. So that means this way of seeing H, you only decide H up to its conformal class. Okay, and this is called a conformal infinity of the metric. In this talk, I will talk about special extension that's called Poincare extension. Rc is equal to -m. Okay, so we are studying this problem. We ask what kind of H allows a G plus filling in, and what is the topology of X relative to M. And the first remark is, on such CCE, it turns out we have a special defining function in an asymptotic neighborhood of M. So this M, this only exists in a small tubular neighborhood. There is an M and then this R. And this geodesic defining function is R squared G plus is a totally geodesic boundary, and I forgot to write down. This R squared G plus is like a product on the manifold in an asymptotic neighborhood. Okay. So this is a cototal, and with respect to the special defining function, this metric is totally geodesic. So let's talk about some example. The obvious example is upper half plane with Rn as conformal infinity. So in the upper half space, we take hyperbolic metric, and then the geodesic defining function is y. Instead, in this case, y squared G plus is the flat metric. It's no longer compact, but frequently this will be the limit of our sequence, blow-up sequence of compactified metric. So this is the model we should keep in mind. And then the real example is hyperbolic ball with sphere. And in this hyperbolic ball, although the defining function r is not that obvious, is 2 times 1 minus y over 1 plus y squared. And writing that down, we have this hyperbolic metric. When we multiply this by r squared g plus, restrict to r equal to 0, we get the sphere GC. That's the canonical metric. And this metric has the particular property. There is a relation between its geodesic defining function and the distance function t in the hyperbolic metric. It's exponential minus t, and which turns out to be an important fact. And we know in asymptotic neighborhood, the hyperbolic distance and the geodesic defining function is asymptotically like this. And now I want to talk about a third example. A third example is if our conformal infinity is S1 lambda, the length lambda cross S2. And then it turns out when lambda is between 1 over square root of 3 over 2, there are at least 3 conformal filling in, and with a different space x. One is x is S1 lambda cross Bn. My n is equal to 3. Okay, so B3. So we develop S2 become B3. And then that's the conformal filling in. And in this case, one can write down the metric. Here is the B3 metric like before. And then on the ds1, we have this parameter distance function, y product with a function. And this metric is hyperbolic, constant sectional curvature, -1. And if we use the familiar coordinate, this r is 2. If we define s to be this way, change this to r, then we can rewrite this metric into this familiar form of hyperbolic metric and y product with the distance function, with the S1. And it turns out later on, if we want to characterize G lambda, is to find the geometric content of what does that S means. Okay. And then there are 2 other metrics with conformal infinity S1 lambda when lambda is small. Okay. And when this is the AD-Schwarzschild metric, I wouldn't want to, so it's written this way. And then we have this horizon when Vm equal to 0. And the important work of Hawking Page is they pointed out for this conformal filling in, for when lambda is small, for the same lambda conformal infinity, there are 2 distinguished fill-in with different mass. The mass is different. Okay, so there's a non-unique filling in problem even with the same space S1 lambda plus S2, and then we develop S1 to become B2, and S2 stay the same. So the space Y is B2 cross S2. So there are 2 different filling in. So the interesting thing now is we look at the boundary S1 lambda cross S1 minus 1. We ask, can one tell the difference between X and Y? And when is it filling X and when is it filling Y? And are these 2 the only topology which are allowed? And these all are open questions. We only very partially address the problem. So recently we obtained the following result. We say, indeed, if we have a Poincare-Einstein filling in with this conformal infinity, and suppose we have the additional property The sectional curvature is G plus. G plus is negative. Then we know the xn plus 1 is already topologically diffeomorphic to S1 cross Bn. And then this G plus is G lambda, the hyperbolic metric we described. So the sectional curvature negative constrain the topology and construct the uniqueness of the extension. And this piece of work uses an early work of Witten and Yao and Chai Galloway to study the fundamental group of the universal curve. And notice that this example, sectional curvature negative, would not be satisfied by the AD as Schwarzschild metric. Okay. And the second theorem we have is, so this says that suppose this condition is satisfied, then we know the extension. And the second theorem says, indeed, when lambda is sufficiently large, given n, we know there is sufficiently large n. When that happens, then indeed this sectional curvature condition is satisfied and the metric is unique. Okay, so we have uniqueness result. And again, this condition is not satisfied for AD as Schwarzschild metric, but an open question we have is, we wonder if this lambda 0 n, we know exists when lambda is very big. So this is my parameter lambda. And when lambda tends to infinity, we know this is true, but we do not know that this can be pushed all the way to 0, even if the topology is the space S1 is equal to S1 cross Bn. So let me say a few words of how the theorem 1 implies theorem 2. Why is lambda big happens, then we know the space of this extension is already X, is S1 cross Bn. And when lambda is very big. This first, we use a well-known fact, a result showing the same result I mentioned before. In this case, the Yamabe constant of S1 lambda, there should be a lambda, Ysn tends to 1 as lambda goes to infinity. Okay. And then the second fact we use is a work of Gang Li, Qin Jie, and Si Yuguang. And they show that in this CCE or AH manifold, there is an inequality. The ball, the volume of the ball is greater than equal to the Yamabe constant to the n/2 power. This constant is the Gromov volume comparison is less than equal to 1. So we have this lower bound. If Ymn is positive, then you have a lower bound. Okay. And then, so in particular, one sees if this Yamabe constant tends to Y, as this happens when lambda very big, the hyperbolic ball become the hyperbolic ball, so we have rigidity theorem. Okay, and to see that happens, we actually say that indeed, when this quotient is very big, not only we control the volume, we control the Weyl tensor. Actually, we control the L2 norm of the Weyl tensor, and that's going to be small. And when Weyl tensor is small, one can see, and we are in a Poincare-Einstein setting, one sees the sectional curvature is in a neighborhood of -1. So it's a negative. So theorem 2 follows from theorem 1. Okay. And now, besides this specific example, let me talk about some general existence problem. There is a general existence in an asymptotic hyperbolic in this asymptotic neighborhood. It should be M, okay, Mn cross 0 epsilon. MM cross epsilon. There exists one, and that's the work of the Pfefferman and Graham M-beam metric construction. And they did it for real analytic metric. Later on, the work of Gursky and Sakidi extend to smooth edge. And then the real existence theorem happens with only very limited knowledge. That is, when the metric is on Sn, when the conformal infinity is the sphere, then in a asymptotically small neighborhood of Hc, you can construct the extension. And in this case, when H is equal to Hc, there is the work of Chang, which shows the hyperbolic extension is the unique one. But it turns out this Lee and Graham, the perturbation result, the metric they construct for G plus with conformal infinity H in a neighborhood of Hc, this G plus is actually in a neighborhood of the hyperbolic metric. And later on, we can show that this extension is also unique. Okay. And then this result also can be extended for n bigger than or equal to 4. But on the other hand, there is also non-existence result. There's a series of non-existence results constructed by Gursky, Han, and Gursky, Han-Strauss. And they constructed saying that, for example, for the manifold M of dimension 4k minus 1, when k is bigger than or equal to 2, for example, S7. And they say in S7, if you consider the space of positive scalar curvature, but if you start it at a component which is not in the component of the canonical metric, then B8 is not allowed to be the compactification of S7. So there is non-existence result. This uses a direct operator. Okay, so there is non-existence result. And now let me also mention another result which is important, and that is on CCE manifold, if the scalar curvature is positive, then the lambda 1 of the Laplace operator is greater than or equal to n squared over 4. There is a work of Melrose, of Mazzero and Melrose, who says in AH setting, I will later mention it, lambda 1 could be less than n squared over 4. But in this case, when the boundary scalar curvature is positive, and from the positive boundary, then lambda 1 is greater than n squared over 4. An important observation made by Chang is this method is a testing function for the eigenvalue. And the testing function Jack Lee constructed turns out to be a geometric content, which I will briefly mention. It turns out what Lee actually did is, given a boundary metric, he construct a conformal filling in with the metric G on the boundary is H and scalar curvature positive. This specific construction is called Jack-Lee construction. So if the Yamabe constant on the boundary is positive, then it's on the interior is positive. This Yamabe constant is a volume normalization Y. Later on, I will mention another Y. Okay, we call this Jack-Lee metric. But still, in view of this counterexample of Gursky, Han, and so on, one can ask, why do they work on S7 and B8? What happened in S3? Okay. In S3, it turns out on 4 manifold, the space of positive scalar curvature is path connected by a result of Marcus. on S3 is path connected. So the counterexample of Gursky-Han would not work. Okay. So one can ask, what happened on S3? And does that, any metric S3 with positive scalar curvature, does that allow CC filling in? And in view of the non-uniqueness problem, the non-existence, non-uniqueness, the question, a more modest question, we approach this question is, instead of asking the existence, we ask the compactness. That is, if we give a boundary, sequence of boundary on a manifold, and suppose we allow HI to have a conformal filling in, does that mean this compactified metric form a compact family? So we approach it by Dirichlet problem. Suppose we have boundary and we know there is an extension inside. Do we have compactness? So that's the problem I'm addressing. Okay, so what's the difficulty of this problem? Now I concentrate my effort when n equal to 3. So this is Mn, M3, and then 4 dimension. In 4 dimension, a compactification has this asymptotic behavior. R squared G plus is dr. This is the geodesic defining function plus the given H and plus G2R squared plus G3R3 and so on. It turns out this G1 is 0 because it's totally geodesic. And G2 is a geometric information in terms of H. It's actually a shortened tensor of H. It's a local term. Local means determined by the boundary data H. But this G3, one can write down, it's a tensor. This G3 is the normal derivative of the shortened tensor. So this is information of S is not completely decided by H. Okay, so we have this non-local term not determined by H. The non-uniqueness problem comes from here. Given H, there could be 2 different S. Okay. So, but on the other hand, the work of Pfeffman, Graham, and later Becquat says G3 and H decides G. Okay. Once you have this Neumann data and the Dirichlet data H, everything is determined. So the question we are asking ourselves address is, we have a spectrum problem. We wonder if our Dirichlet data, given that it has a special structure, is conformally compact, Einstein compact, does that already decide the Neumann data? Does the Dirichlet data plus the structure see the Neumann data? That's the question we are addressing. And now, that's the problem we are addressing. And then how do we address the problem? We have this H given, and then we want to decide this class of metric H. And then the problem is, what is a good representative of H? And what is a good, this is modular conformal class. What's a representative of GI? The classical way of approaching, the most natural way, is consider H to be the Yamabe metric on the boundary. And then there's this Yamabe metric on the interior. But the problem with that is we do not know how to connect the G Yamabe metric, the boundary behavior of that, to HY. We do not see it. So we need another approach. And this approach now, the way we approach is through scattering data. So let me mention what the scattering means. We construct, given H, we construct the extension. So this construction is by solving this PDE. this Sn minus S is the eigenvalue lambda. So we are talking about Poisson equation. And in this Poisson equation, we know that the early work of Melrose and Mazzero says that except for finite many of point spectrum, this problem is solvable. Except for finite number of lambda, this is solvable. And now, once one solves this equation, so I'm looking at this equation, minus Laplace plus u minus S1 minus Su equal to 0. I'm looking at this equation, and then it has asymptotic data, Rn minus S and Rs scattering. These are Rn minus S, Rs is the approximate solution, so we write that down. And this Dirichlet data F is given by R to the n minus S, S minus n times U restrict to the boundary. F restrict to the boundary is my given data F. Okay. So given this Dirichlet problem, that means we give this F, we solve this equation, and then we look at the data, and that's the Neumann data. The Neumann data is called the scattering operator. The scattering metric S restrict, sending F to G restrict to the boundary is the scattering data. So this scattering data turns out to have a very important conformal invariant property. If we write S equal to n over 2 plus gamma, and then the operator defined by the scattering data at this particular point has a conformal covariant property. So it's an operator which has this generalizing when gamma equal to 2, this P2 gamma is the P4 operator earlier I talked about. But this operator now is defined on a spectrum on all gamma between a parameter 0 to n squared over 4. And this is a P2 gamma operator. When gamma equal to integer, turns out to be the well-studied, this Grand, Jenny, Manson, Sparling operator studied in conformal geometry. But this approach says in this setting, we actually have fractional Penney's operator. And this has a continuous parameter of operator satisfying this property. And now, using this information, we now, given an H, we can construct many extensions. And one observation is when lambda 1 is bigger than n squared over 4 minus gamma squared, this Vs, by solving that with Dirichlet data 1, is strictly positive. So that means that when RH, his boundary is positive, remember Jack Lee says this lambda 1 is greater than n squared over 4. So for each gamma, we have a solution of this equation, Vs, a family of solutions. And we define this rho S to be Vs to the 1 over n minus S power. So the offshot now is for each S, we have an operator Gs star. Gs star restrict to the boundary is given H. Okay, but we have a parameter of family. And for this operator, it turns out if we take S equal to n plus, we call this metric the adapted metric, that the Dirichlet data and solving the equation. And when S equal to n plus 1, so we write this S equal to n over 2 plus gamma. Gamma denotes the order of the operator. But when S is n plus 1, S is equal to n plus 1. This turns out to be the metric constructed by Jack Lee. That is, when the scalar curvature on the boundary is positive, one can directly check the scalar curvature is positive on the interior. But it turns out, after much playing, the operator we are interested in is S equal to n/2 plus 1 half. Let me say why we are interested in this particular index. For this index, the associated scalar curvature is 0. Scalar curvature 0. So in this case, this G star, the scalar curvature is 0. And under the assumption the boundary is positive for all, the mean curvature is positive. It has this good property. The scalar curvature is 0, the mean curvature is positive. And then additionally, it also has the advantage when n equal to 3. When n equal to 3, we can use Gauss-Bonnet formula. It turns out in this case, one look at the Gauss-Bonnet integral. If the value is in L2, then the total curvature of this metric is in L2. That's the important property we want. We cannot see it from other parameter, but we can see it from this parameter. The total curvature is in L2. But it turns out in this analysis, we need to pass information at S equal to n plus 1 to n/2 plus 1 half. When n equal to 3, so we are passing 4 to 2. Okay, and we need to analytic continuation, meaning of the metric, which is a Jack-Lee metric, passing it for this particular one. And the huddle comes out to be equal to S(n/2) plus 1, plus n/2 plus 1, plus 3/2, I'm sorry. So equal to 3, when n equal to 3. So we have a huddle here. And what is that huddle? That is the scattering operator has a pole there. So the property passing from the Jack-Lee to our adapted metric, we need to cross this pole. And this pole turns out by solving this equation and then take DDS as dot equal to 0. And this is a metric studied by Pfefferman-Graham. That's the Pfefferman-Graham metric. This is the Lee metric. Okay. Pfefferman-Graham metric has the good properties Q flat. Q curvature is flat. Q curvature is flat. So many of the analytic property is crossing from this to there by passing this Pfefferman-Graham metric. Okay, so with this, I can now state what's the theorem we obtain. The theorem we obtain is, suppose we consider this sequence of adapted metric, which is scalar flat. Scalar flat. And then we construct a solution, we call it GI star, by solving the PDE. Then if the boundary is CK, boundary is bounded away from 0. And we want to say that this GI star is compact. But first, we need to add some topological assumption so that this sequence of metric does not have interior blow-up. So this topological constraint is to prevent interior blow-up. And then we add some condition, which is Weyl curvature in L2. We would rather not add this condition, but at least this condition is a conformally invariant condition. So it's a natural to the property. Adding this Weyl curvature in L2, then we reach the compactness problem, compactness of this sequence of adapted metric. And that's the work of myself and Yuxin Ge. And let me just say one word about what is essentially what we are doing. Essentially, what we are doing is saying this scalar flat metric has the good property, which is if Y is in L2, then its curvature is in L2. So its blow-up limit, rescale blow-up limit has a curvature decay property of order delta for some delta positive. And this curvature decay property allows us to study the limiting metric and to draw that a contradiction argument saying it reaches to hyperbolic space and its G infinity is the half Euclidean space. In this case, the scaled metric G infinity plus is the limit of that G infinity, conformal infinity, because we keep on scaling this sequence of HI, which is already compact. So the limit reaching on the boundaries are 3. So we reach the model which we desire. And that's the difficult part of the proof. And we need to gain regularity passing from one compactification to the other. In particular, we use this Q-flat property essentially to gain regularity, and that is because there's a work of Fang, Wang, and Zhu, both are in China, and they show that once one family of GS star is compact, so is the other family. Okay, so we play with this interrelation of this family and we reach the compactness. Okay, so let me say existence result. For that, we reach an existence result that if H and HC is less than constant, then for the only thing I want to mention is this is not an asymptotic result. Reach a definite step. If an HC is 10 to the 10 to the minus 6 power apart, but a definite number, then we reach the existence result. I'm sorry, I ran out of time. And the key estimate of this part is why is this allow us to estimate this S tensor? And this is through some work of BKN and so on. Sorry, I'm running out of time. So so we begin to estimate this S tensor by studying the corresponding PDE, and then we reach the compactness estimate. We have this Y1 and Y2. Y1 is the Yamabe constant with normalized volume. Y2 is the Yamabe constant normalized surface area. And we get global control Y1 and Y2, both in terms of Y. And from there, we get an S estimate. So I'm sorry I ran out of time. Let me just mention that open question we are working on, and we do not know if we get answer. The question is this L2 bound or vial condition necessary? And we are working on this problem. Okay. We want to see if the Dirichlet data already have a priori estimate of L2 of the vial curvature. In the case of Ricci flat metric, this is the work of Neighbor and Neighbor and Chiger. Okay. But we are in a conformal compact Einstein setting. So thank you for your attention.
Very nice talk. So any questions or comments?
If you start from the physics perspective, then the scattering matrix would satisfy certain conditions, like positivity conditions. Do you think that would be useful in finding existence and uniqueness?
Say that again, I'm sorry.
If one starts from physics perspective, because many of the things you described have a physics interpretation in terms of correlation functions in the dual CFT. and that implies conditions on the S matrix you discuss. The question is whether, for instance, there are positivity conditions that this matrix should satisfy.
We don't know. We are looking at the ADS Schwarzschild metric very carefully to see what happens. Yeah, we don't know. The answer is we don't know. Yeah, especially if this allows filling in with singularity. So there's this topological constraint which doesn't allow the interior singularity. We don't know what is the condition. Yeah. Okay, sure.
Any more questions? So maybe I have one. So if the for manifold is algebraic, is there any implication of this conformal invariant on the complex algebraic surface?
I don't know.
Okay.
There are certainly people working on many aspects of it. Yeah, many aspects of it. Yeah, including the recent work of Jun Hong. Yeah, he's studying this guarding inequality and then the sigma k invariance in a very algebraic surface setting.
Okay.
Yeah.
Okay. Yeah. Thanks. So, any more questions? If there are no more questions, so let's thank the speaker again.